Go for it, Genesis generators. Take it away.
Okay. We are the Genesis generators, and our project covers melanoma tumor size prediction. I just want to point out the background. I really like it because we created it ourselves. We didn't find it from the internet. I'm very proud of us there. Can you scroll down? About our project. Welcome to our project. Today, melanoma remains the third most common type of skin cancer worldwide. As such, healthcare professionals seek a way to find a treatment early before it becomes fatal. In this project, we aim to utilize coding languages such as Python and HTML to predict the size of melanoma tumor based upon its characteristics. It is our hope that our model can help healthcare professionals identify melanoma tumors as early as possible so it can be treated with no further complications. Our goals, what we aim at with our project. Discover what determines melanoma tumor size. Use graphics to determine how 9 different factors affect the size of our tumor. Train a machine learning model. Make a machine learning model that predicts the size of a melanoma tumor. Aid the healthcare industry. Create a simple, easy-to-use website that can detect patterns within different factors.
Our MVP, or minimum viable product, will have like graphs and like charts and characteristics such as like the damage size, exposed area, and like the tumor size of melanoma tumors. And our product will be able to make like accurate predictions of the size of future melanoma tumors based on these characteristics. So onto the tech stack. What we used to make our project is like HTML, CSS, JavaScript, and like other programming languages in order to make like an easy to use like GUI to interface with the Python backbone. We used pandas for data management, NumPy for mathematical operations, sklearn for the machine learning model, and Plotly and Seaborn for graphing our data. So this is a list of variables that will be like seen in the graphs and in like the machine learning model. Some of them, just to list them off, are like damage size, which is unrecoverable area of skin damaged by the tumor, exposed area, which is the total exposed area to the tumor, and damage ratio, which is the ratio of damage to total spread on the skin. Now, you should make note of them because you might have to come back to understand more of the graphs and the predictor. So on to Riley with the graphs.
Alrighty, so our first graph is a scatter matrix, which is like like a bunch of scatter plots put onto one scatter matrix. They display the correlations between each of our variables. So like for instance, the top graph, it shows the size of that's the graph of the size of the area and then the mass of the area. And as you can see, as the size increases, the mass also increases. You can also see that the size of the tumor is also displayed. As you can see from the red dots, they indicate higher tumor size, and then the green dots indicate a lower tumor size. Our next one is a scatter plot that shows the correlation between the malignant ratio and the tumor size. And according to this, as the tumor size increases, the malignant ratio also increases. And then our next graph is a density heat map. It's similar to the scatter plot because it shows the correlation between the malignant ratio and the tumor size. But this one also counts how many of the tumors share the same tumor size and malignant ratio. So the lighter dots indicate a higher count of tumors that share the same size and malignant ratio, and then the darker dots share there are less amount of dots or tumors that share the same size and malignant ratio. I'll hand it off to Enzo for the rest of our graphs.
Our next graph is a 3D model that's interactive and compares exposed area, malignant ratio, and mass NP, and you can hover over each of the dots and see the individual details of them, as well as move around the graph. We also have a second graph under it that compares exposed area, damage size, and malignant ratio, as well as tumor size with color. Our next graph is a violin chart, which shows how often the damage size appears. So the wider sections of the graph indicate a higher amount of a certain value, and the narrower sections of the graph indicate a lower amount of a certain value. The next graph is a parallel coordinate chart, which shows how each variable changes as the tumor size increases or decreases. The green lines indicate an increase in tumor size, and the red lines indicate a decrease in tumor size. Our next graph is a correlation heat map, which is similar to a scatter matrix because it displays relationships between each variable. And the lighter colors represent a greater correlation between variables, and the darker colors represent a lesser correlation between variables. Our last graph is a density contour, which kind of looks like Scotland, but it shows the distribution between damage size and tumor size, with colored contours becoming brighter to portray the higher density of tumors at that contour.
In week 1, we began by finding a data set and learning Python. We also met each other for the first time. In week 2, we began making graphs and models. We cleaned our data and we prepared a machine learning model. It began designing a website, create an interactive user interface to interface with the predictions. This actually become what it is today. Now handing it over.
For our machine learning models. So we used a regression problem. Since the value we're trying to predict, the tumor size, is continuous, and so it's not a classification problem. And then because we found our model that was already because our model data that was already labeled, this problem is an example of a supervised machine learning. And then we had 5 machine learning model options, but from there we only used 3. We used linear ridge regression, which is a model estimating the coefficients of multiple regression models. And when you have the data in which multiple independent variables are correlated. And then we use the gradient boosting regressor. It finds the difference between the current predictor and the known target value. And so it trains the weak model to correlate to the target value. Handing it off to Malvika.
Our third model is the decision tree regressor, which trains a model in the structure of a tree to predict data. Now that we figured out our top 3 models, we had to figure out which one was the most accurate for our data. To do this, we looked at 3 different values. Root mean squared error and mean squared error both measure the difference between the actual and predicted values, so we would prefer lower numbers for these values. R squared measures the proportion of values that can be predicted accurately by our model, so a higher R squared is preferred. These graphs clearly show that linear ridge regression is our most accurate model, since it has the lowest RMSE and MSE as well as the highest R squared. In conclusion, we found that most of our features, excluding damage size and damage ratio, have a positive correlation with tumor size. We also found that the most accurate machine learning model for our data was the linear ridge regression model. We hope our findings will help the healthcare industry in the identification and classification of melanoma tumors. In addition, we created a live interactive predictor, where the user can input values and get a prediction using our most accurate model, the linear ridge regression model. To test this, would you guys like to give me some values to input into each of these fields, or if you prefer, I can just choose randomly. All right, 1, 2, 3, 4, 5, 6, 7, 8. I'll do 9. Okay, so as you can see, with these values for each of these variables, our model has predicted that the size of your tumor is 61 point all of these numbers. Now, Jasper will finish off this presentation by introducing our amazing team. As soon as it loads, just give it a second.
This project was made in great part by Aarush, Felix, Jasper, Riley, Enzo, Malvika, and Samuel. Thank you for listening.